Now, for a very long time, we thought that light was a radiation, correct? Light was behaving like a wave. So, in the early 1900s, so we discovered that light also behaves like a particle. So, a radiation behaves like a wave as well as a particle. Around 1920s, so there was a French physicist called as De-Broglie. Now, he put forth a very bold idea that even a particle behaves like a wave. Wave was behaving like a particle. Experimentally, we proved it. What he told was the vice versa. That is, a particle is behaving like a wave, or a particle behaves like a wave. Now, this became a very bizarre idea. Like, how can a particle behave like a wave? How can a person be a wave? It's not possible, right? So what he made was a hypothesis. What he told was, suppose we have a particle with a mass of m moving with a velocity of v, then we say that the De-Broglie wavelength is lambda is equal to h divided by p, where p is the momentum. Momentum is what? M into v. So here this gives a relation between the mass, which is a particle parameter of any part, like you can say it's a parameter relating to a particle, correct? Or lambda, which is a parameter relating to wave. So what he told was, any material which has a mass of m moving with the velocity of v has a wavelength of lambda, which is h divided by p. Okay, so and he also gave something called as relativistic mass. That is, as the particles move with a very high speed, the mass of the particle will change. So what he gave was m is equal to m naught divided by root of 1 minus v square divided by c square. Now here v is the velocity of the particle which is moving, c is the velocity of light, and m naught is the rest mass of the particle. Alright, so this is the formula what he gave for relativistic mass of a particle. Okay, so he gave certain explanation. That is, one, as the particle is smaller and smaller and smaller, then the De-Broglie wavelength is more and more and more. Okay, so lesser the mass, more is the De-Broglie wavelength. The second is, so as the particle moves faster, then also the De-Broglie wavelength becomes higher. Okay, so these are the two things what he gave, or you can say experimental observations based on this whatever hypothesis he gave. Like experimentally they verified it. Fine. Now to back up Louis De-Broglie, this was around 1920s, around 1920, 1924. Now to back up his theory, there was another physicist called as Werner Heisenberg. Now Heisenberg's famous thing is Heisenberg's uncertainty principle. So what does this principle state? So it states that at the same time, or you can say at the exact time, it is impossible to detect the position and momentum of any particle. Okay, so exact position and exact momentum. So mathematically we can write this as delta x into delta p is less than or equal to h divided by 2 pi. Fine. So what he told was, suppose let's say I need to figure out where the electron is. Let's say I'm looking under a microscope, an electron microscope. So if I need to figure out where exactly is the electron, then I cannot figure out what is the momentum. Okay, so position we can find out, but not momentum. Suppose if I can figure out the momentum, then I cannot figure out where the electron is. So at the exact same time, we cannot figure out the position as well as the momentum. So this is Heisenberg uncertainty principle. So to back up Louis De-Broglie's wave nature of matter, this Heisenberg's principle also came into play. Okay, so whatever Heisenberg did, lots of people try to experimentally prove it, in which two of them succeeded. So what they did and how did they experiment, you'll see in the next video.